Welcome back. In this session, we are expanding our API system by walking through two vital backend challenges. First up is structs and JSON wrong keys on the wire. Instead of diving blindly into the files, let's use the DVL AI chat to methodically prompt engineer our way to the problem area, exactly how technical interviewers expect you to operate. First, let's open the AI panel and ask our initial discovery prompt. Where are the API routes and what do the data models look like for the book's endpoint? The AI instantly directs us to API/books.go. Now let's follow up by asking, what do the tests look like for this module? The AI points out tests/books_test.go, warning us that the front end expects a strict data contract of snake_case JSON keys and explicitly requires an empty array, not a null value, when the bookstore collection is completely empty. Let's analyze the underlying concepts before writing code. Before fixing the bugs, it's vital to understand how Go handles serialization under the hood. Go's standard encoding/JSON package relies entirely on runtime reflection via the reflect package to examine the structure's metadata. By default, unless told otherwise, it marshals fields using their exact public Pascal case names. Furthermore, we must understand memory allocation for collections. In Go, declaring a slice like var books, book allocates a header whose internal data pointer is explicitly nil. While a nil slice behaves gracefully in pure Go logic, the JSON encoder translates a nil pointer directly to the primitive JavaScript value null. To satisfy strict API contracts, we must forcefully trigger a memory allocation to instantiate an empty, non-nil slice descriptor. Let's jump into the code to apply these principles. Zooming in closely on our structural type declarations inside API/books.go, we see our book struct uses standard public fields, capital ID, capital title, and capital in stock. Because they lack explicit metadata instructions, runtime reflection is dumping raw Pascal case keys onto the wire. Let's fix this contract precisely. We will append explicit struct tags using backticks. Right next to each field, we write JSON : followed by the snake_case keys in quotes, ID, title, author, year, and in _stock. This overrides the default reflection mapping. Next, let's scroll down to our collection endpoint handler, get/API/books. Notice the logic flow. The handler safely locks our store mutex, but then directly passes store.books to our JSON utility. If no books exist, store.books is an uninitialized nil slice, forcing the encoder to emit null. Let's fix this fallback logic. We pull the collection into a local variable called books and implement a defensive initializer check. If books equals nil, if that evaluates to true, we explicitly overwrite it with an empty allocated slice, literal using books equals open bracket, close bracket, book open brace, close brace. Now, when passed to our right JSON helper, it safely marshals as a clean, compliant, empty JSON array. Let's pull up our terminal panel, execute our Docker test suite, and watch the output. Fantastic. Every single test passes flawlessly with 100% full credit. We successfully secured our data contract using structured prompt engineering and solid Go fundamentals. With our JSON contract completely secured, let's transition straight into our next challenge: validation. Trust, no input. Once again, we leverage our DVL AI assistant rather than guessing our architecture layout. Let's open our chat interface and query, where are the API routes and what do the data models look like for the signups endpoint? The assistant highlights API/signups.go. We follow up immediately with, what do the tests look like for this module? The AI alerts us that the post handler at /API/signups is currently wide open. It accepts empty usernames, garbage emails, and underage applicants, committing them straight to memory. The tests require us to enforce a strict validation guardrail before data persistence ever occurs. From an architectural standpoint, input validation represents your first line of defense against data corruption and security vulnerabilities. Industry standard practices dictate a fail-fast or circuit-breaking approach. Instead of executing expensive operations, grabbing memory locks, or writing payloads to database structures prematurely, your application logic must intercept incoming payloads right at the boundary. By verifying structural criteria instantly and executing early returns with explicit 400 bad request states, you isolate the underlying system memory and critical routines from malicious or malformed input. Looking closely at API/signups.go, we see that the body is unmarshaled, but immediately after, it acquires a mutex lock and persists the data blindly. Let's build our defensive validation pipeline. First, we must handle structural parsing failures securely. We change the blank assignment to an explicit conditional block. If ERR equals read, JSON, not equal nil. Inside, we respond with a 400 bad request and an invalid JSON body error string, followed by a hard return to stop execution. Next, we stack our business rules sequentially. Rule 1. The username must be at least 3 characters. We write, if len ... username less than 3. If triggered, we emit a 400 status with an explicit error message and return immediately. Rule 2. The email must be valid. We use the standard string utility by writing, if not strings point, contains open parenthesis in point, email comma, string literal containing the symbol @. If the check fails, we issue a 400 state and return. Rule 3. Age enforcement. We add, if in point age less than 18. Again, we intercept with a 400 response and an age requirement error message, followed by an immediate return. Only when every single circuit breaker passes cleanly do we allow the code to proceed downward to acquire the mutex lock and commit the clean, verified payload to our persistent store. Let's pull up our terminal panel, execute Docker Compose test suite for module, and watch the test log spin. Sensational. Every single test, the sign-up validation guardrail passes flawlessly with 100% full credit. By applying disciplined prompt engineering strategies and rigid defensive programming principles, we transformed a fragile API layer into a rock-solid, production-ready system. See you in the next session.